Now we're going to go over one of the more one of the um more obvious. Sorry, my brain just went dead there. Yeah, so now we're going to go over one of the more obvious and more useful applications of waves, which is waves traveling along a string, like you might see it for a guitar or a harp or a piano. So basically, what happens when you do a little flick of the string, uh, you find that between some delta x, there's going to be tension force pulling to the other side of the string that's going to be equal to each other. And then there's going to be some force pushing up and some force pushing down, which aren't going to be equal to each other. But the ratio of F1 over Ft and the ratio of F2 over Ft, where Ft is the tension force, are equal to the derivatives of the string at that period, where Ft over F1 over Ft is negative dy dx, where y is the height of the string, or like how displaced up the string is, and F2 over Ft equals positive dy over dx at x2. So the F net is going to be equal to F1 plus F2, which is just Ft times those derivatives minus each other, which is going to be equal to Ma, or mu, which is the mass per unit length, times delta x, which is going to be equal to delta m, times d squared y dt squared, which is a, which is just the definition of a. So you divide both sides by delta x and ft, and you'll find that the change in dy dx over delta x equals d squared y dx squared by definition, as delta x goes to 0, is equal to mu over the force of tension times d squared y dt squared, which is just the wave equation, right? So the wave, it follows the wave equation as you send a pulse or a sound wave, or not even a sound wave, a sine wave, or anything like that along the string of your guitar or piano, then it's a wave with a velocity of the square root of force tension over the square root of force tension over the mass per unit length. So this is why when you play a string, you're able to get those sound waves to come out so clearly and like express themselves as pure sound waves or pure sine waves, because the definition of a wave appears when you try to solve for the force. And this works in general for different types of objects, where V is going to be the square root of the elastic property over the inertial property, where, for example, we have force of tension, which is going to be what keeps it moving up and down over the force per, or the mass per unit length, for a one-dimensional string. Or if you're talking about 3 dimensions, you have V equals the bulk modulus over the density, which is the mass per unit length or mass per unit volume. So this is just how strings work. Yeah, that's just how matter travel, or waves travel through matter. And that's pretty important, I think. But that's going to be all that I have to say on that. I'm going to come back, I think, 2 more times. All right, thank you.